Um, Good evening, everyone. Now, today we will move to a new model, which is thin wall T-section cantilever beams. We will model this cantilever beam by using a shell element available in ABAQUS. This beam is a cantilever. The length of the beam is 1.2 meter, and we have a point load 4 kN applied on the tip of that beam. You have 100 millimeter by 100 millimeter dimension, and the full thickness or all the walls, the flange and the width by 5 millimeter. Now we need to model this beam using a shell element S8R, which is 8 noded shell element available in ABAQUS with a quadratic element. And the number of element is 32 element. Basically you will have in the width you have 4 elements. In this flange here and this flange we have 2 elements, and also we have 1, 2, 3, 4 elements in z-axis. After we do the modeling, we need to find out the vertical displacement U2 along AB, the bending stress S11 along AB, bending stress S11 along BQ, which is in the middle, the shear stress along BQ, and therefore after shear stress you need to find out what is the shear flow, and a shear stress along SRS, and you need then to find the shear flow, and hence let's write it, and hence PQ long RS. Okay, that is finite element modeling, and then you have to do the theory to compare between finite element modeling and the theory. And based on the theory, you need to find the deflection, the bending moment, the bending moment around AB, along PQ, and the shear flow distribution along the width and the flange together. Now, how we start to model? First of all, keep in mind the length of that cantilever is 1.2 meter, and also the material property is 200 kN per millimeter, which is Young modulus. And then you must know that the dimensions are 100 by 100. So assume you have for example the coordinates at this point here. Therefore, based on this coordinate, you can draw the section. Now let's start. Let's go to ABAQUS. We'll write to start and write ABAQUS. And ABAQUS CAE. We wait the ABAQUS to run. Now choose the standard explicit model. Before we carry on, we need to set a directory. So when you set a directory, go for example in your directory into C, new PC, and data, and then for example set a directory of, create a folder and call this folder as ABAQUS ABAQUS T-section. Okay, let's call this folder, we keep it. Now we go to File, Set Directory, Work Directory. The default is on C, and you don't want this default, and you click on to select. You go into D drive, that's where you saved your model, your file, and then you go, where is the file? Data one, ABAQUS T-section. Don't double click, just only click that you set directory, so the whole file will be saved on that folder, and then OK, and then OK. Now we start the model, we go to part, we go into create part. Let's call the part as T-section. It's a 3D. It is a shell element. Since a shell element, and what we will do, we will basically create the section and extrude it. So we'll do an extrusion, and then we continue. Now, let's start off by drawing the web. The coordinates of the web 0, 0 and 0, 100 on that point. So you click on the line, create line connected. So write down 0, 0 and 0, 100. Now, if you do an auto fit, you will see the line of the web. Now, what you have to do then, you cancel the procedure for this line, and then we need to draw another line, which is the web, the flange, and the flange start from the point from here to here, and the coordinate of this point here, we assume it as 50 by 100, here minus 50 by 100. So you click on the line again, so it is 50 and 100, comma, no, enter, and then minus 50, comma, 100, enter. You click on the cancel procedure. Now, if you notice that we've created the T-section with the web and the flange, and if you do done, we'll ask you to extrude the section. Since the length of the beam is 1.2 meter and we are working in millimeter, so it's 1200 millimeter. So the length is 1200 millimeter, and you click OK. And now you find out your T-section. Let's get and save it. Again, we're gonna save it. Let us see section. And OK. After we create the part, we need to create a material property for that part. You go here and you go to property. You go into material manager. You click. And then you create, in the material manager you create. Now, let's call this as a steel material. It is elastic material, so we go to mechanical, elasticity, and then elastic, which is 200,000 with Newton per millimeter squared, and 0.25 as a material property here written here, and then OK. Now you create the material property, and let's dismiss. Now let's go to section manager. Now we need to create a section, and I go to create. Let's call it a T-section. We call it homogeneous and solid. Sorry, homogeneous and shell, because we are working in a shell element. And type is homogeneous. Because since we are working in a shell element, so we need a homogeneous. And then we say continue. Now what we have to do, the value of the shell thickness is 5 millimeter as expected. Keep in mind that sometimes could have the flanges and the web has different thickness, so we have to create two different sections. Now since the flanges and the web has the same thickness, so we could create only one section. In case we have the flanges and the web as different thickness, so we need to create two sections. Now we have the same thickness, so we can have one section here. If you have different thickness, so you need to create another section for that particular thickness, and you continue and you write a new thickness. Why you cancel? Because we have the same thickness. Now you go to assignment manager and you go to create. We'll ask you which element we need to which area. Let's click all this area by making this window, because all the flanges and the web has the same thickness. And then click on and then done. We keep the same defaults here. Since we have only one section, that's enough. And OK. And then done. Let's close these. We don't need it anymore. Let's go to assembly. Since we have this beam is not ready assembled, so we need to bring it into the model. So you go to here, create this instance. Now we will assume that I want independent instance. We're not independent instance. And then we said OK. Don't say apply, said OK, that you bring it. Now save if you want, and then go to step. Let's go into step manager. The reason we need a step is because we care about having load step, because the load will be applied in a step. You create step manager and then you go to create. We keep the name as it is, general step static we will use, and continue. Now since we are doing a linear elastic analysis, so we don't need to use any type of incrementation. Also we are working toward have small small displacement applied, so we don't care about having geometrically no linearity, so we keep as a default as it is. For more details about it, more options, that will be given the next few lectures. And then OK. And then dismiss. Now you go into your loading, the load. Let's create a boundary condition on the left hand side here. To create a boundary condition, you go to your boundary condition manager, and then we'll create. Let's call fixed boundary condition BC, and let's choose the second option, and then let's continue. Now we will ask you here which dimensions, where do you want to put a boundary condition. I want to put a boundary condition on here, here, and these flanges, because there are 3 edges. So if you click on one and then I want to click the other, you deactivate the web. So what we have to do, we click on the web and then press shift on your key to select more than one element and release after you finish selecting. And then you said, okay, done. That's the elements. Then what you have to do, you click all over here, all, to show that you have 0 in all dimension, all node, all degree of freedom. And then you said, okay, and just close it. Now pay attention to the note we keep saying in a class, which is zooming in and out by rolling your your mouse wheel. So by rolling your mouse wheel, so you can zoom in and out, and also by clicking the rotate view, you can rotate your model. So please practice this. In order to cancel your rotation, you need to cancel the procedure, and you can now zoom in and out. Now I need to put the point load in here, and you have a load manager. You create, let's call it as a point load, sorry, and then this concentrated load, make sure this step is step 1, and then you continue. You click on this point where you want to apply a load, and then done. Now since we have a load goes downward in y direction, if you look in this coordinate, it's so important to look on this coordinate, or you can look on this coordinate or this coordinate. You have 3 coordinates, so you can always see plotting. And then you click here, which is in y coordinate with CF2, and then you apply -4,000. It is 1000 because we are working Newton, and convert it for kilonewton to 4,000 Newton, and it's minus because it's downward. And then you said okay, and you will see the sign here, the arrow for the loading, and dismiss the load. Now let's go to mesh. You go to mesh. Where do you have the mesh? Now let's make sure that we understand the meshing. We have, for the flanges, we do have 2 elements in that direction, and for the web we have 4 elements. Now let's go to the flange. You click on the seed edge. Now since this web, this edge and this flange and this edge has the same number of mesh, so we'll click on here, and then I click shift, click here, and then click here, and then click here, and then you have say done. By clicking number and choose 2 elements, I said okay. If you have this flange has a different number of elements from this flange, so you have to select this, and then you have to select this element. Now you need also to mesh the web, so you click on this edge and shift in your keyboard, and then click here and then done, and choose a number of OR, and then okay. And now lastly we have 4 elements in that direction, so you need to find the whole edges. So instead you can make a window in the middle, somewhere in the middle of the beam. So if you notice that this line is selected, and then you say done, and you choose the 4 elements, and then okay. You see that triangle and the dot, or the blue dots, which is show that you are seeding a nodes around this section. Then done. After that, you click on the mesh part instance to mesh it, because you are seeding the node but you didn't mesh it. And then you said yes because you need to mesh the stuff. Make sure that you have the correct number of node elements, and I think is yes. And then we need to assign what type of element we need to use. Let's click, and then it choose the element, and then done. Make sure you are using shell, and we need to use a quadratic, which is the element we are working on with the S8R, which is doubly curved thick shell. Doubly curved thick shell. And then OK. And then OK. After we finish the mesh, let's run the model. You go into job manager, and then you create, and this is your job. You don't need to call it, name it, and then continue, and then OK. Submit the model and wait for. Now get the result. And then, and to show the deformed shape, that is your deformed shape that I've got. Now, I make a table here to find the deflection along AB, to find the bending stress along AB, bending stress along PQ, and shear flow along PQ, and finally shear flow along RS. Let's start with this. Let's start with the deflection along AB from here to there. Let's go to U, and which is U2. The same way, go to Tool, Create Path, Manager, and then create. This is path. For example, let's call this is path for deflection, or PQ. Let's call it PQ. This is our PQ here. AB, sorry. AB, and then continue and add after. You click here, there. If you find difficulty to find a node, especially in the middle here, you can go into common option, click on the labels, tick here the show nodes label, and say OK. It will show you actually the node label, and then you click there. We can move the model using pan view, and then cancel it, and then OK. So to find a node, yes, this one, and then this one, or zoom out and zoom in, this one, and I finally zoom out, zoom in, and this node. I think done. And we've got the nodes all, yes, done. And that's it, and then I said okay. And dismiss. Now, you go to Tool, XY Data and Manager. Again, Tool, XY Data, Manager. Let's create an XY data and then from path. We need to find from path and continue. Now, that is your path AB. We're gonna take undeformed shape because we're taking the absolute distance. And since it's in which distance? This is in distance Z, so you get this distance. The value of X, which is Z distance. Make sure this is U2 and then save as and OK. If you double click here, you will get your displacement. Let's take this value of the displacement, copy them, and then paste them in your table. This is very small value. Make it as a 0, and this is the rest. You need to compare it with the theory later. Now, let's think about the bending straight along PQ. So we're gonna create PQ. Now, okay. In order to do that, let's close this. I close this. We are going to find, we need S and S11 are the bending stress. Now, let's create a path over PQ in the middle here. You go to Tools, Path, Manager. Repeat it. Path, Tools, Path, Manager. Create. Let's call it PQ. And then continue. And add after. Now what you need here these nodes. Click from below to top to this element, this element, this element. I don't see the element, so I need to move it a bit, rotate it, cancel procedure from the rotation, and we continue. Click, click, click. I think you can see it. Yes, this click. That's a vertical node. So zoom in, zoom out, and then done. And then OK. You go now to Tools, XY Data, Manager, Create, get the path and continue. You need PQ and the bending straight over PQ. And PQ is in Y direction, so you have to Y distance. Make sure this is S11 and say save as and then say OK. Just double click. You get the whole values of the bending moment. Copy these values and go and copy them and put them actually in AB, here and here. That is over PQ. Ctrl Z. This is here, PQ. PQ. That's one. So that's the value of the PQ, bending moment of the PQ. And then you have to compare it with the theory. I've done the theory actually here. And you have it in your note. Right, the value of the theories. Now, what I do need now, I need the shear flow in PQ. Again, this is shear flow in PQ. How to do that? Again, you go here. Let's click it, close it. Make sure we have S12, which is a shear stress. And this shear stress is along PQ. We keep it as a PQ. And then save as. And it said OK. Double click. That is your shear stress along PQ. This is shear stress. And I copy. And go here and paste it along shear stress along PQ. However, these are shear stress. In order to get the shear flow, you multiply the shear stress by the thickness. So that's your shear stress, shear flow. And you can compare it with your finite element, with your hand calculation, which is, I already did it here. That is my hand calculation. Sorry, this is my hand calculation. And you can compare it with the hand calculation in here. Okay? With the theory. Fine. Now, what we've got? We need bending stress along AB, and this is very tricky. Now let's talk why it is tricky here. Go to your model, close everything here. Now, so you need S and B S11. Now, rotate a bit and look at it. Let's turn off actually the nodes labels by going to label and then OK. Now we need to find out the shear stresses along AB. Think about any of these points. Let's say this point. You see this node is connecting between this flange, this element, second element, and the fourth element from the web, third element for the web. So this node connected between three elements. Again, this element, this node, is connecting between 1, 2, 3, 4. And also, if you rotate it here, 5, 6. So this is node connecting between 6 elements, 4 from the flange and 2 elements from the web. Now we are in S11. If you go to query information, this is important to remember it. Query information. You click. This is a general query, so you know something. You can use it to find out some value of the node. And you click the node and prop values. If you only move, sorry, before that you need to, your prop has to be a node, not element. Now, if you move a little bit to it, you will see at least 6 values. Now the question is, what are these values for? Why did we have a lot of these values? Because this node is connecting between four elements from we have a 4 element share the same node from the flange, and 2 elements share the same node with shear element. Yeah, sorry, we have 6 elements sharing the same node. So we have 6 values. And you notice the value 87.12 and 87.1251, it seems are the value from the web, and minus 7.81984, 4.57395, etc., are the value from the flange. Now, we are finding them, and we are interested mainly on the value of shear bending stress S11 along the joint AB with respect to the stresses in the web, because it's a maximum web. So whenever you get the maximum web is the maximum value of the stress is the one we are looking for. So whenever you have here any value with the maximum stress is the stress in the web that we are care about. If you go to here, for example, we will pick up the maximum stress with a 115, which is a stress in the web. If you go here and you go there, this is a maximum value of stress, which is 58.4588, which is the stresses in the web. Okay, now let's close it. We already create a path. So let's go to Tools, XY Data, Manager, and then create path, continue. You need it AAB, make sure this is S11, and distance is in Z distance, don't forget it. And then save as, and OK. If you double click, you will notice this issue. The 7.9, this is for the distance 0, this is for flange, and 115 this for what the web. 1.102 is this is for the web, this is for the flange, this is for the flange, this is for the web, this is for the flange, this is for the web, this value the stress at the flange, etc., etc. So the maximum value of these will be the value for the web, and that's the value we are working on use in our calculation. So let's copy these all, copy, and go to Excel sheets, and let's say paste. Now let's, as we discussed, we said we use the maximum value of stress in our calculation, which is the stress at the web. I will delete this, and for 150 millimeter I will delete this, and then I will delete this and this value, and then for this value I will delete this. For 600 I will delete this value. For 750 I will delete this value. For 900 I will delete this value. For 1050 I will delete this value, and 1200 delete this value. So these are the maximum values for the distances, and then let's move it back here, drag it here, take it here, let's take it here. Let's copy them, and we need to put them on AB bending stress. Okay, now in conclusion, if you want to find the bending stress along AB, you take the maximum value of that bending stress along AB. Isn't so? We take the maximum value of the bending stress found along AB. The last one, which is RS. We need to find the shear flow around RS. What we have to do again, we go to our model, let's close this, and then we change from S into S12. And what we said, it is along RS, and then RS from this horizontal over flange, so we need to create a new path. We don't have this path at all. So let's close this and let's go and create a new path. Here, go to Tools, Path, Manager. Then you create, let's call it RS, and continue, add after. Now just click here, here, okay, and then done, and then okay. Let's go to XY data, Tools, XY data manager, that's already open, and then create, click path, continue. I need RS, which is in X direction. Make sure this is undeformed, S11, and save as, and OK. Let's double click, and we get the value. But you notice something interesting, which is a 50, it's repeated 4 times. And for each value of this, we have different values. Why? I'll tell you why. If you go to, and at the distance 50, it is this node, which is a shear node between 1, 2, 3, 4 elements from the web, from the flange. If you click on I here, click in the node, prop value, if you drag it a little bit here, you'll find minus 9.36, minus 9.36. All these values are for the web, and the rest of this value 4.56, 4.71, minus 4.71, minus 4.5 are value from the flange. Now close it. Now you know where is it come from. In our example here, they take the value from the flanges. So, and also interestingly, that 4.5 and 4.7 from this flange, right flange, left flange, left element of the flange, and left element of the right element of the flange. So the value is positive here, and the value seems negative here. Now let's just choose the maximum between the negative and positive value. So let's copy paste, copy these, and let's paste it here. Now we will choose positive, negative values here. So for example, I will delete this one and this one. I will keep 4.7 and minus 4.7 in our calculation. Let's run this way. And what we can do is, if delete this one, this value, this can be written as a plus minus. Plus minus. Let's copy this and paste it on the shear flow. And let's write, I think it's hard to write it plus minus. It is a plus, comma, again, minus 4.71447. I don't make a problem. Plus minus think I know to do it somehow by insert equation and then plus minus. Let's bring this well, the equation here. Maybe somewhere. It's our plus minus here. Now, the shear flow, we multiply it by the thickness. Copy and paste.